Well, hello there. The one missing ingredient from the set of tools that we need to develop the rest of the curriculum for the entire semester is Newton's third law, or the idea that's commonly called Newton's third law. That's assuming that you already know your calculus. If you've got your calculus down, all you really need are Newton's second law, Newton's third law, and the universal law of gravitation. And from those, or from that short list of ideas, you can develop everything that happens in this semester. So let's consider a person who is just starting off the blocks in a sprint race. And actually, let's pretend that there are no blocks. It would be simpler to just imagine that she starts running on a flat track. And let's assume that she's accelerating in the forward direction. So her center of mass, because I should point out that we've been talking about really point particles thus far. A baseball is easily modeled as a point particle. The human body is more complicated because you can move your arms and legs and change the configuration. You can change your shape. But there is a special point within your body called the center of mass, and that's the point that's accelerating forward, let's say. And now we can introduce Newton's second law, specifically along the horizontal axis. So I will call this direction the x-axis. And we know that if there is an acceleration along that axis, there must be a net force. So where does the force come from that propels this woman forward as she begins to sprint? And it's fairly obvious that it has something to do with her. She's the one kicking with her legs or pushing down as hard as she can. But remember, in order to accelerate something, a force must be applied from outside that thing. So if the m in F equals ma is the mass of her body, then the force must come from outside her body. What could possibly be pushing on her in this direction? That would have to be the force that we call friction. We call it friction because it's parallel to the surface. We know it's parallel because that's what Newton's second law says. If the acceleration is forward, then the net force must also be forward. Let's look at the y-axis now. There's no reason in this frame, this picture, to expect that she would be accelerating up or down. She's not jumping off the ground or allowing herself to fall. So let's just make the assumption that a sub y is 0. In other words, the net force in the y direction must be 0. So let's look at the forces that might be acting on her vertically. Obviously, there's the ever-present gravity force, or at least in this class, we think of gravity as a force that would pull straight down. And don't get hung up on why I chose to put the tail of the vector here. It's mostly just for aesthetic considerations. At this point in the semester, we don't really care where the forces are applied on an object. We just care how strong the forces are and the direction. Later, when we talk about the rotation of a rigid object, it will matter where the forces are applied. And we'll be talking about something called torque. Whoop, I got ahead of myself there. If gravity were the only force acting on her in the vertical direction, then we would have to conclude, we would have to conclude that there is an acceleration downward. You see that? Wherever there's a force, there must be an acceleration. If the only vertical force on her body was down, meaning gravity, then she would have to have an acceleration that's down. But by assumption, she's not accelerating. So there must be a force that points in the opposite direction with the same magnitude so that the total force is 0. And we tend to call that the normal force because, again, normal is just a word that means perpendicular. A line that's perpendicular to a plane is called a normal line. So I went ahead and made sure that this arrow has the same length as this arrow, but points in the opposite direction, so that when you add the two, you get 0 as required. So if this woman weighs 120 pounds, if gravity is pulling down on her with 120 pounds of force, then the track must be pushing up on her with a force of 120 pounds. Now, how did I get from there to this slide? Well, again, the net force, the net vector force. So now we're looking at the overall vector. We're not restricting ourselves to x or y. When you add up these three vectors, these two sum to 0. You could say they cancel in air quotes. And if these two sum to 0, then we're really just left with this. And so we can rename the friction force F net. Makes sense. Remember, net force is proportional to total acceleration. So they have to point in the same direction. Now, if we go back to this picture, the friction force. That's what pushing on what. We know that's the track pushing on her foot, or you could say the track and foot pushing on each other, perhaps. That's really what we're getting at here. The normal force is what pushing on what. That's also the track pushing on the foot. So the normal force is the track pushing straight up on her foot. The friction force is the track pushing forward on her foot. So they're really two components of a single interaction. There's really just, you could think of it as one interaction force between the track and her foot. And if these are the components of that interaction, when you add those components up, this would be the total force of the track on the runner. So this is a subscript convention that we'll use frequently from now on. F sub TR means the force of the track on the runner. And it actually points forward and up. It's got this oblique direction. Not only does the track need to support her weight, it's got to balance the gravitational force, it also has to provide the forward acceleration. But we like to call the parallel component here friction, and the normal component we just call the normal force. Okay, I'm going to scoot that over. So this is where we have to wonder, how do you get the track to push on you? The track is inanimate. It's not alive. It doesn't have moving parts. There's no motor or belt or pulley, no gears. It's just a flat thing. So how do you get it to push on you, and to push on you with just the right magnitude and just the right direction? So maybe this sounds like a stupid question to you, but of course you get the track to push on you by pushing on the track. You can feel it when you run. You slam your foot down, the various muscles in your leg engage, you're pushing down on the track while simultaneously pushing back, if you think about it. So I've made a bold assertion here. I've made a bold assertion here that the force of the runner on the track, that's FRT, perhaps should have the same magnitude. See, the length here is the same as the force of the track on the runner, and the opposite direction. It seems reasonable, at least. If the track, in order to get the track to push in this direction with this exact magnitude, perhaps you have to push in this direction on the track with the same magnitude. Now, I say bold assertion, but I'm obviously not the first person to suggest this. This is what we call Newton's third law. Newton may have been the first person to really recognize this necessity and to put it in words. And we can do better than putting it in words. We can actually express it with an equation. So remember, if I write something like this without the vector symbol, I'm talking about the length or magnitude of the vector. So according to this picture here, the magnitude of the runner's force on the track should be the same as the magnitude of the track's force on the runner. Is that true? Well, if it's true, we could also make this stronger vector statement. Not only are the magnitudes equal, but the vectors are equal with a minus sign. Right? When you say that two vectors, or that one vector is the negative of another vector, that means it's got the same length. You've just turned it through 180 degrees. You flipped it around. That's what the minus sign does. So is that true? It seems like a reasonable assumption. I mean, what else would you conclude here? You know, is this yellow arrow going to point off in some other direction with some other length? That would be difficult to justify. This at least seems like the most likely explanation. One way you could test that, well, hypothetically, take two people, maybe they're in a zero gravity environment. Fine, let's just pretend they're out in space with space helmets, but I didn't draw the helmets. And they've got their feet up against each other, and they're both gonna push off from one another and try to push away. So this red arrow shows Rudy pushing on Carl. I had to pick some names to assist with this discussion here. This guy looks like a Carl to me. So this is the force of Rudy pushing on Carl. Now, for a moment, let's just suppose that it's possible for Carl to push harder on Rudy. He seems to be the bigger individual. So I've indicated that with a longer arrow. And I certainly, before having studied physics, I would have thought that this is possible, that if you're a bigger, stronger person, you can push harder on the other person than they're pushing back on you. So let's suppose that that's the case, that there are two different force vectors here. One that describes this one-way interaction, Rudy pushing on Carl, and the other describing Carl pushing on Rudy, and suppose that those vectors can have different lengths. Well, again, these individuals are not particles, really. They're extended masses. They can change their shape, but there is a special point called the center of mass, and we know that as they push away from each other, those two centers of mass will move outward. And something we can show later in the semester is that F equals ma can be applied to their center of mass. So the net force on Rudy would be her mass times the acceleration of her center of mass. So we'll just track the acceleration of that dot, or that little square that represents her center of mass. And each of them should have a center of mass that accelerates away from the other person. So this is Rudy's acceleration, and this is Carl's acceleration. Now, if they're out in space and there's no gravity, no air drag, then really the only force on Carl would be this force, Rudy pushing on Carl. And the only force on Rudy would be this force, Carl pushing on Rudy. So we can apply Newton's second law now to each of these people. Here's Newton's second law applied to Rudy. The only force on Rudy is Carl pushing on Rudy. So that should be Rudy's mass times Rudy's acceleration. Oops. And let me back up here. Same thing for Carl. If the only force on Carl is Rudy pushing on Carl, then this really is the net force. And we know that the net force on Carl must be Carl's mass times the acceleration of Carl's center of mass. And here's where we can put Newton's third law to the test. Because mass is something that can easily be measured, maybe these two people were weighed back on Earth, and conceivably you could measure their acceleration as well. Maybe there was some way of determining where the center of mass of their body is, and then following that in Tracker, or an even better application. So it's definitely possible to determine the product of mass and acceleration for both individuals. No problem there, theoretically. Well, Newton's second law, which we have ample evidence for now. Hopefully you've got some gut sense that Newton's second law is legitimate. It does a great job of predicting the motion of material objects. If Newton's second law is true, then we can easily determine what the force on Rudy would have to be. So if Rudy has particular mass accelerating at a particular rate, then there must be this force on her body. And then we could just ask, do these forces come out the same? And all experimental evidence indicates the affirmative. It doesn't matter how much stronger Carl is than Rudy, or vice versa. If they push off from each other, and you carefully measure the product of mass and acceleration for each individual, you will find that the two forces are the same, which may be a little surprising. You can't push harder on somebody than they're pushing back on you. Now, who's doing the pushing? You know, what if Rudy just kind of locks her legs and rests there passively? So Carl's really the one doing the pushing. He's the one exerting effort with his muscles. Well, if you're Rudy, even if you're not actively flexing your muscles, you still feel the push on your foot. So they would still experience the same force on the soles of their feet, no matter who's doing the pushing. Let's carry this forward. Here's an actual image I found of an X-ray of somebody's foot inside a shoe. And you can see this picture must have been taken a while ago, because this is not a Nike here. We're looking at some old-fashioned shoe. You can even see the metal fasteners between the heel and the sole. I don't know a lot about this, but you can do some Googling. I believe it used to be relatively commonplace in big cities to have shoe stores where you could stick your foot into the shoe and actually look at how well your foot fit using an X-ray machine. Like you would view your shoe in real time. And I'm sure it wasn't long before they discovered the negative consequences of that. It's kind of ironic that the same technology, X-rays, which allows for this photograph, probably produced tumors, which could be seen with that technology. In any case, suppose that this foot is resting on the ground. Here's the ground. And we know that the ground has to push up on the foot. So this is the force of the ground on the foot. Now, really, doesn't the ground push on the foot at multiple points of contact? You've got all these points of contact at the heel. Let's just sum up all those individual forces and call it one net force upwards. And by the same token, the foot would have to be pushing down on the ground. And what we're trying to explore in our minds right now is whether those two forces should be equal. Does the foot push on the ground just as hard as the ground pushes on the foot? Well, here's one way of thinking about this that should also help make Newton's third law seem plausible. Let's look at the sole of the shoe, which lies between the foot and the ground. And I'll just represent that with this simple rectangle here. So this is the bottom of the shoe. And if you're standing there, if this person is standing there, then the sole of their shoe is in equilibrium, meaning it's not accelerating, meaning that the net force on it must be zero. And let's not worry about the weight of that sole because it can't be very heavy. So the only relevant force is, whoops, I feel like I'm missing, no, this is the slide. So look carefully here, or no, I guess I have to fix this. I thought I had dropped a slide, but this works. So I've actually drawn the force vectors now with their tails at the place where you can imagine the force is applied. So let's look at the top of the sole here. I've got the tail of this vector right here. The foot pushing down on the ground, well, really, the foot is pushing down on the sole of the foot. So I could have relabeled this force of the foot on the sole, but the magnitude of that force should be the same as the force of the foot on the ground. And then the ground doesn't actually push directly on the foot because they're not in contact. The ground really pushes on the sole. So I've drawn this vector with its tail here to indicate that's where the ground actually pushes on the sole of the shoe. And presumably that force would be the same as the force of the ground on the foot. You know, if you remove the sole from the equation and imagine they were standing there barefoot, however hard the ground pushes on the sole of the shoe, that would be the same as how hard the ground pushes on the foot. Okay, but the conclusion is because the sole of the shoe is in equilibrium, those two forces must be equal. So by introducing this intermediate mass, the sole of the shoe, we've made it very plausible that those two forces would have to be equal in magnitude and opposite direction. That's one way of applying Newton's third law to this situation. Okay, now earlier I was asking, how do you get the track to push on you if it's an inanimate object? If it's just flat, how does something push on you, right? If it doesn't have muscles and moving parts or moving parts. Well, it's a little easier to understand if you imagine something like one of these exercise bands. And I think it's kind of creepy that this person is faceless, so let's give him a face. I'm not sure that's any better. And let's focus just on his left hand. So we all know from experience that in order to stretch this elastic band, you would have to pull outward. So here is the force of Tom on the band, the elastic band. That's Tom pulling on the band. And why does he have to pull outward on the elastic band? Of course, it's because the band pulls the opposite direction on his hand. And you can feel that when you stretch it. So it's more concrete in this instance. It's easier to understand how this inanimate object that doesn't have moving parts could actually apply a force on you. It's because you've stretched it. When you stretch an object, or many objects, they tend to pull back towards the center. So it's that displacement or stretch that's produced, or that allows the inanimate object to exert a force on you. And it seems reasonable that if the band is pulling inward here with 20 pounds of force, you would have to pull outward with a force of 20 pounds. So the forces would be equal and opposite. And of course, the same thing is going on the other hand. And it doesn't have to be stretching. Imagine if you had compressed a spring. Now, this spring is probably too stiff to be casually compressed with your hands like this, but let's just suppose that this spring is normally a little bit longer and this person has compressed it, and we know that the spring will push back. So here are the vectors representing the spring pushing back on the hands, both hands. And we could call those forces force of the spring on the hand. So it's an inanimate object, but why is it pushing on you? Because you have compressed it. That's easier to understand than how a track pushes up on your foot. And of course, to keep it compressed, you will have to balance that force. You'll have to push back on the spring. This is the force of the hand on the spring, just as hard as the spring pushes on your hand. And so we can identify what's called an action-reaction force pair. This is a common phrase used to explain Newton's third law. If this spring is pushing back on your hand with 10 pounds of force, then you must push on the spring with 10 pounds of force in the opposite direction. And something that's very important to recognize about an action-reaction pair, these two force vectors do not act on the same mass. This vector is a force applied to the hand. This vector is a force applied to the spring. So when you do a free body diagram, you're looking at all the forces on a single mass. So you would never have an action-reaction pair show up in your free body diagram for a single mass. That's an important thing to keep in mind as you're setting up these dynamics problems. And now maybe it's a little easier to understand how something else inanimate, like a bed or a mattress, could apply a force on you. I didn't draw the force vectors, but gravity, of course, is pulling down on this woman, and that means the mattress must push up to support her weight. Now, I think most mattresses don't necessarily have springs in them. Maybe they do, I don't know, but some mattresses do. Now it's easy to understand how that mattress pushes up on you when you're lying on it. It's because you have compressed the springs. So there's some deformation that's gone on to produce that force. And now it's not much of a logical leap to understand how if a springy bed can support your weight, then maybe something like the floor could support your weight. When you're just standing on the floor, how exactly does it support your weight? If it can't be compressed or stretched and it doesn't have moving parts, maybe it actually can be compressed. It's just imperceptible. So let's imagine somebody standing on the floor, and I'm just modeling the floor as being made of a bunch of springs. We know that something like a wooden floor doesn't have springs in it, but it's made of atoms and molecules, and perhaps those have spring-like behavior. So here's Adam Sandler standing on the floor, and I've indicated, let me go back and forth here, no atom with atom. You see how the floor has been compressed slightly? I've compressed all these springs. Maybe when you stand on the floor, just beneath your feet, there's a very imperceptible compression that allows the matter of the floor to be spring-like and push back on you. So this would be the force of the floor on Adam. This force is the result of the compression of those springs. And then, of course, Adam would have to push back on the floor. I have not drawn the gravity vector or the gravity force on Adam because I'm looking specifically at the action-reaction pair that we assign to the interaction between Adam and the floor. Adam and the floor are interacting via this action-reaction pair. Now, again, this is not something you notice. You'll notice it if you stand on a trampoline. That one's obvious. Or a mattress. But when you stand on tile, laminate, wood floor, you don't notice the compression. Do you think if you could somehow stand in the same spot as a rhinoceros? Fine, I guess I'll indicate that this force of the floor on Adam, again, that's what we call the normal floors. Maybe if you had a much more massive object on the floor, the compression would be more obvious. I think even on like tile floor, you're not going to noticeably see, like a concrete floor, you're not going to see the compression even from the weight of a rhinoceros. Maybe if the rhinoceros were wearing high heels, and so you were concentrating that force on a small area, maybe you actually could see a depression in the concrete. I know I should have a graphic for that, but I don't. So in this case, because the compression is much greater, you would expect a much greater normal force. This is a topic for later in the semester, but the more you compress a spring, the harder it pushes back. So if mattresses can push on you by being compressed or deforming, and if even the floor or the ground pushes on you by experiencing a compression, maybe all kinds of contact forces that we're familiar with and haven't thought much about actually involve springiness and compression. Here's a great example.
Come here with good stuff, leave with broken stuff. Ready?
Whoa. I'll make sure that's on.
Ball's coming in hot.
I'm way up front.
Excellent, guys.
It almost almost like
Not my bad.
kind of comes back out.
Oh my gosh, you can see the compression moves to the ball.
It's like a sponge.
Whoa, did you guys see that? There's a bend in the back. Look at that.
See it flex there.
Yeah.
The sand kind of wobble.
And then it
Yeah.
wobbles for a couple seconds.
Yeah.
Seconds is the wrong word.
So it's very clear there that the baseball can be squished. Impossible to do with your hand. I doubt any of us are strong enough to hold a baseball and noticeably squish it. But when you give it momentum and the bat's got momentum and you allow them to collide over a short time interval, you get these tremendous forces that are sufficient to compress the baseball. So I didn't draw force vectors, but if these two are interacting with in a way that could be described with an action-reaction pair, you've got, can I back up to where they're actually in contact? So you've got the baseball pushing to the right on the ball. You've got the ball pushing to the left on the baseball. Well, if you just set a baseball in your hand, it's not going to push on your hand very, very hard. In fact, the push on your hand is just the baseball's weight. But presumably, the force between these two right now is huge. It's probably hundreds, if not thousands of pounds. My guess is over 1,000 pounds. So how can the baseball possibly push on a bat with that kind of force? Remember, it's an action-reaction pair. The force vectors would have to be equal. So if the interaction force is over 1,000 pounds, how do you get a baseball to push on anything with 1,000 pounds of force? Well, it would have to be compressed by that much. Just think of it as a spring that's going to push back real hard. If you actually could squish a baseball with 1,000 pounds of force in your hand, you can imagine that the baseball would be pushing back on your hand with 1,000 pounds of force. There's some more evidence that contact forces involved deformation. Something has to squish or bend or change shape and to act kind of like a spring. We can't leave out this one. Now, what else can we say about Newton's third law to make it more believable, seem more plausible, and maybe even more obvious? Let's consider a collision between a golf ball and a ping pong ball. So the ping pong ball was moving this way, the golf ball was moving upwards. And as they collide, they will exert forces on each other. This is the force of the golf ball on the ping pong ball, and vice versa. And let's not forget that golf balls and ping pong balls, like every object around us, is made out of ordinary matter, ordinary atoms, and you learned in elementary school that atoms have positive and electric charge. So here's my silly picture of the particles making up the two objects. I'm just representing them as these diatomic molecules here. It's not really important to our discussion what type of molecules they are. We can zoom in here. And again, molecules are made out of atoms. Atoms are made out of positive and negative charge. That's a trivial result for all of you. Hopefully you learned that well before college. Maybe you didn't. But what is it, 120 years ago? Which is really not that long ago. That was not at all common knowledge. So it's pretty recent in human history that we've discovered the existence of these two opposite charges within all matter. So I've represented that charge with these little plus and minus signs. And I'm just trying to illustrate that if you zoom in closer and closer on the boundary between these two objects, you've got a collision between individual particles, each of which consists of a balance of positive and negative charge. And what do we know about the interaction between individual charges? So never mind the particles themselves, because remember, if we're talking about oxygen, for instance, I think each oxygen atom's got 8 protons. And did I get that right? I think it's atomic number 8. So 8 protons and 8 electrons and some neutrons. Let's just focus on the interaction between individual protons or electrons. This may be something that you're familiar with. We know that like charges repel. So if you brought two positive charges with equal charge, let's say 2 protons, near each other, they would push away from each other, and presumably this one would be pushed just as hard as this one is pushed. Hence the equal and opposite arrows here. So when it comes to the interaction between identical charges and their electrical repulsion or attraction, Newton's third law seems really plausible. It almost, seems like the only sensible result. Now, over here we've got a plus and a minus, so these are different particles, but the attraction between them still involves equal and opposite force vectors. So again, we're postulating that the attraction or the interaction consists of an action-reaction pair, even for this fundamental interaction between charges. So Newton's third law can apply all the way down to the most fundamental interaction you can think of. Well, I should qualify that because particle physics does go further even than just protons. We know that protons are supposedly made out of these things called quarks, but let's keep it simple for now. And when you take electricity and magnetism, you will actually learn the very simple force law for the attraction or repulsion between those two charges. It looks an awful lot like Newton's universal law of gravity, but instead of talking about masses, we're talking about charges. And instead of talking about a gravitational force, we are talking about an electrical force. But I would like to point out at this time that it's easy to conceive of a scenario where the interaction between two charged particles, that's the most fundamental interaction we're talking about here, does not consist of an action-reaction pair. This interaction between one charged particle moving to the right and another charged particle moving up, so it's headed towards this one. They're not actually going to collide because by the time this one gets here, this one's already over here, but they're crossing the T, so to speak. Once you learn the laws of electricity and magnetism, you will be able to see that the force between these two does not consist of an action-reaction pair. In fact, if we label these charges A and B, the force that charge A exerts on B actually points to the left. You might be thinking, wait a minute, shouldn't it point down? Hang on a second. I realized as I was staring at that slide a day after making it that I may have forgotten some aspect of the interaction there. So most likely the force of A on B would point in this direction. There's a magnetic force you would have to take into consideration and an electrical repulsion. And when you add those two together, I'm assuming you get a result like this. And when you apply the laws of electricity and magnetism to find the net force on A, you would find probably something like that. The magnetic interaction goes away, and you would just have that electrical repulsion. Now, I'm not maintaining that I've faithfully determined correctly determined the direction of the forces there, but the qualitative result I do know is correct, which is that those two force vectors are not equal. You've got two particles in motion with respect to each other, and their velocities are not parallel. And this is one situation in which, if the laws of, again, we call them Maxwell's equations, if the results of classical electrodynamics are applied correctly, one finds that the two force vectors are not equal and opposite. So it's not hard to imagine a situation involving fundamental particles and an electric charge where the interaction cannot be described by a simple force or action-reaction force pair. So to summarize, it is not necessarily satisfied by the interaction between two charged particles which are in relative motion. That's the key. If they're moving with respect to each other, things get more complicated. However, in this class, mechanics, we typically don't have to worry about that because we're talking about macroscopic objects colliding with each other, rigid objects or mostly rigid objects, which involve contact forces. So in the hit, during a baseball hit, yes, the baseball is moving and the baseball bat are moving, but as long as they're in contact, then when you look at the surfaces where they touch, there's no relative motion. So they're moving together. We don't have to deal with the complication of charged particles moving orthogonally or with velocities that are not parallel. So if you put yourself in the frame of reference of that point of contact, then the particles in this surface and the particles in this surface are moving together, or I should say in their frame of reference, they're not moving at all. There's no relative motion. So that complication goes away. In this class, we always just assume that Newton's third law is obeyed. Okay, now that we've got some visceral sense of the content of Newton's third law, let's look at how a leaf blower works. We don't need to know the details, whether it's a gas combustion engine in there, 2-stroke, 4-stroke, or it's an electric motor, it doesn't matter. The whole point of the blower is to force air out of the tube there. And so we imagine those particles moving their way away from the blower. Now, the actual interaction between the air particles and the motor happens somewhere in here, of course. Maybe there's a turbine in there, an impeller, propeller. I don't know what the word is, but the interaction happens in here. And once these air particles acquire their velocity, they just continue on out the tube. But since it's inconvenient to draw them in here, let's just put them at the end of the tube here. And I've drawn the force of the blower on the air. This is the force of the Milwaukee brand blower on the air. Never mind the fact that that force is applied somewhere in here. Well, if the blower is pushing on the air, then the air must push back on the blower. And again, I'm not getting hung up on where that force is applied. I put the tail of this vector way over here versus over here. It doesn't matter. For this discussion, all we care about is the fact that those two force vectors are equal in length and opposite in direction. So if this blower is applying a net force of 25 pounds to the air as it launches the air out the tube, then there must be a reaction force. You could even call it a recoil force on the blower backwards. And anybody who's used a blower, I'm sure, knows that. And you could call that thrust. You could call the backwards reaction force on the blower thrust, which is a suggestive word because we know that rockets experience thrust. And a rocket works much the same way as a blower. It ejects fuel particles one way, and the rocket receives a thrust in the opposite direction. So I would call this force the thrust force or the reaction force. It's the reaction against the force applied to the air. And if you're skeptical of that force because you've never actually used a leaf blower, I think I can provide some proof to you.
All right, let's do it.
So in case it's not clear there, it looks like they have removed the extension, but the air will be ejected from this leaf blower to the left. And here's the battery pack.
No, we can take it down towards me. All right, I'm gonna throttle up. We're gonna go. Yeah, it's actually not flying as well as it did yesterday.
They're like the Wright brothers, but with the leaf blower. So if it's possible to do that, then do you think this is possible? So what can we say about this setup using our understanding of Newton's dynamics or Newton's laws? We know that in order to eject the air, the blower must apply a force to the air. So I'm using this yellow vector to represent the force applied on the air leaving the blower. Let me get my laser pointer. And consequently, there will be a reaction force, the other half of that action-reaction pair, and I will call that the force of the air on the blower. So the air has to push back on the blower. That's the same action-reaction we were talking about just a moment ago. But once that air leaves the blower, presumably it's going to be traveling quickly. That's the whole point of a leaf blower. And it will collide with this umbrella, which is acting a lot like a sail. It's like he's a little boat, or he's in a little boat, which is the bucket here, and the umbrella is his sail. And as that air crashes into the sail, it should apply a force. So this is the force of the air on the umbrella. And now let's just isolate the forces that are acting on him. And by him, I really mean him plus the bucket plus the blower plus the umbrella. All of those things are attached. So the M in F equals MA will be the janitor plus the bucket plus the blower and the sail, which he's holding. The air is really separate because the air is not attached to that system. It's free to move away from the bucket, janitor, umbrella, blower system. So let's remove all forces, or really let's remove the one force in this picture that's not a force directly on that system, and that would be the force on the air. Let's just look at the forces on the janitor. And the only forces I see would be the air pushing back on the blower, and he's holding the blower, so that's really a force on him. And then the air pushing against the umbrella after it's been ejected from the blower. Because he's holding the umbrella, that's really a force on him. And I'm under the assumption, or I'm working under the assumption here that those forces are basically equal and opposite. So yes, if he's holding the umbrella and the air is crashing into the umbrella, he ought to receive a forward push, like wind pushing on a sail. But we can't forget about the reaction force on the leaf blower. And if those two cancel, then it really would not be possible to obtain acceleration in this way. The net force would be zero. So have we been duped? Well, if you go back to the beginning of the video, you can see when he first plops down the bucket, in the very next frame practically, look at that, the wheels are different. He seems to have mounted the bucket on an electric skateboard. And I'm gonna admit, I was bamboozled. I wasn't aware of these electric skateboards, so it didn't occur to me immediately that that was a possibility. And I think he's just pretending even to pull the starter cord and put gas in it. It is a hoax.
Charlatan! Charlatan!
So does this mean that it's not in fact possible to achieve acceleration in this way? Can you not move a boat forward by blowing on the sail yourself rather than relying on the wind? Well, here's a truly awesome YouTube channel by a guy named Bruce Yeany who teaches 8th grade physics, or at least used to teach 8th grade physics. He may be retired now, and yet he has produced some of the highest quality physics demos I've ever seen, and there's tons of them, dozens. So check out his channel if you're curious. Let's see what he has to say about this matter.
Today in Homemade Science, I want to take another look at my fan cart. Now in the previous video, I had some demonstrations that I think I could have done better. Plus I got some great suggestions in the comment section of a few things that we can try. So I thought we'd take a closer look. Now the fan cart's a very popular demonstration that's done in the science classroom. In fact, I borrowed this one from our high school physics room. Now the device demonstrates Newton's third law. When I turn this on, the fan's going to be pushing air in that direction, which in turn is going to give us a reaction of the cart moving in that direction.
Okay, so if you want to connect that with what we were just looking at, this is the mop bucket, and this is the leaf blower pointed that way. You know, in the leaf blower video, usually the guy was moving to the right. Let's pretend that the janitor is facing to the left. He's got his leaf blower pointed to the left. And if he didn't have that umbrella, or if it wasn't a fake, it looks like his mop bucket would actually be pushed backwards, which does suggest that you could get around on that mop bucket just by using a leaf blower, but you wouldn't need the umbrella.
Now the next part of this demonstration is to add this piece of plastic to the cart, and this plastic is going to act as a sail. If air hits it, well, that's going to drive the cart in this direction. And the fan, of course, wants to drive the cart in this direction. So with the sail in place and the fans turned on, what happens?
Okay, classic demo. So that leads you to think immediately that it shouldn't be possible for that janitor to actually propel himself forward in that way. Yes, the forward push on the umbrella would tend to accelerate the mop bucket forward, but don't forget about the reaction force on the blower. And it looks like from this demo that those two forces would cancel. Or would they necessarily?
It stays still.
So this cart doesn't move because both those forces are applied to the cart itself. And they're equal. There's no net force to push it in one direction or the other. Now I decided to make my own fan cart, and it looks like this.
I shaped it like a boat so I could demonstrate the misapplication of Newton's laws in a children's story, and also in some cartoons.
So this is exactly what the janitor was pretending to do, right? The roller skates here are basically the mop bucket. The fan has been replaced by the leaf blower, and the sail here would be his umbrella. So this ruse is an old one.
Now since the previous video, I have added a stronger motor, and I had quite a few questions about my sail and the way I positioned it. So if I put it in this direction, it's pretty much acting as a solid piece of plastic. Let's see if it makes any difference if I turn it around.
Even with the sail on the correct side of the mast, the sheet is simply pulled too tight to make any difference. It's just simply directing the air off to the sides. What is needed is a curved surface that can redirect the air backwards, kind of like the reverse thrust on a jet engine.
So my next step was to make a sail out of cardboard, which I thought could then deflect some of the air backwards, enough so that it would be able to drive the cart
And you'll notice this looks a lot like the umbrella, doesn't it? The curvature.
forward. And when I turn this on, we see that it worked. So the question I got asked over and over in the comment section was, could I do that with a cloth sail?
What? Wait, does that mean that it wasn't fake? I'm pretty sure it's fake. We saw the electric skateboard underneath the bucket, but here's a proof of concept. Is it actually possible to accelerate yourself in this mop bucket with an umbrella like that?
I thought I'd better give it a try since that's what they showed in the drawings. Well, actually I'm going to use plastic instead of cloth since that's easier to use.
I think we're ready to give this a try here. Face it. And off it goes.
Amazing. So if you're like me, at this point, you just wanted to bang your head into a wall because at first I got excited by the video of the guy with the umbrella, and I sat down to think about how to explain it because it didn't seem plausible. It seemed like there was a violation of Newton's third law, or really a violation of momentum conservation, which is something we'll talk about later. And so I was relieved to discover that it was fake. And then here's this guy showing us that it is possible. So I thought about it some more, and it turns out it's really not that mysterious. Later in the semester, we'll be able to use notions of momentum conservation and energy conservation to explain how this works. But basically, it's really no different than just propelling yourself backwards with the fan alone. Just get rid of the sail. You could get propulsion that way. The sail just redirects the air in the opposite direction.